Welcome friends, my name is Muhammad Fazlur Rahman and I am M.Tech in Aerospace Engineering. I deliver lectures in the field of aerospace sciences and deal mostly in aerodynamics and propulsion area. Today we are going to discuss about the jet engine and its technological advancements, and we'll try to see how the engine works, its classification, and different types of engine. We'll try to have a small idea about them, and then we'll actually see how they have advanced from scratch to what we have today. We'll try to have all our discussion in 3 phases. In the first phase, we'll try to get familiar with the aircraft engines, and we'll see other engines also than jet engine and see their advantages and disadvantages. Then we'll just look into the genesis of the jet engine and see a brief timeline through which jet engine has grown from nowhere to what we have today, and then finally we'll just try to look into the advancements the jet engine technologies we have seen. Now let me start with the aircraft engines. In the aircraft engine, I ask a question: what is engine? Engine in general is a device which can convert from one form of energy to another form of energy. But in today's date, this definition has become much more wide, and it has included so many different things which were looking very I'm not very comfortable, but they call it engine. Like if I'll give you an example. In HAL we had a project where we are working with aircraft simulator, and then Simultech Romania, he sent one guy to train us on one of their software which we are going to use by embedding in our software, and they call that their software as the simulation engine. It was doing some kind of simulation. So it was taking a lot of inputs from the aircraft particulars, and then it was giving some output, and those output were used by our programming to do the simulation. They're calling it engine. That's also engine. But in today's discussion, when we say engine, we will particularly mean to the heat engine. The heat engine in which the heat is taken as input, and then an output as the kinetic energy is given to it. So that is our engine in today's discussion. Propulsion is the core of flying. Why I say this thing is that people were having good idea about the aerodynamics by looking at the bird's feather and all. They knew that they need this kind of a structure to fly, but flying could not been possible until recently in the beginning of 20th century, because propulsion available at the time was not efficient enough. The most powerful propulsion available we had at the time was the steam engine, and that engine could actually generate a lot of thrust. A huge amount of thrust is possible, but it itself was huge and bulky. So the amount of thrust produced by this bulky engine was not good enough to take it along with other part of the vehicle and go into the air, get airborne. That's not possible. So for propulsion or for flying, what is required was not just the thrust, a high thrust, rather a different parameter we are looking for, and that was we call as a thrust to weight ratio. So an engine should give a good thrust, a good amount of thrust, but at the same time it should have a small weight. If an engine gives a huge thrust and itself has a huge weight, that reduces its usability in the aerospace vehicles and all. So steam engine was not possible anyway. When the petrol engine came, petrol engine gave a sufficiently good amount of thrust to weight ratio. A good figure was available with it, and that became possible to be used in the aircraft as engine. Thrust to weight ratio is important. Now let us classify the engines. We have broad way two types of engine: air breathing engines and non-air breathing engines. Air breathing engine, by saying name itself, gives an idea that it breathes air from outside. So air is utilized to oxidize the fuel of the engine. For this, they breathe air from outside. The non-air breathing engine does not breathe air from outside. It means it carries all its oxidizer along with itself. The advantage of non-air breathing engine is it can even operate in an atmosphere, in an environment where there is no air. That's not possible for the air breathing engine. So these two advantages are there. But one more point we can mention here is the non-air breathing engine can actually operate in a non-air environment, but since it has to carry all its propellant, we'll say propellant means is oxidizer as well as fuel along with itself, its range is low. It cannot operate for a long time even in air because it doesn't breathe air. It has to carry both by itself. So in air, in airplane where we fly, it's always good to use the air breathing engines unless we need some high speed where rocket engines are employed, like in missiles and rockets as a weapon. In all airplanes we use air breathing engines except a few. This flow diagram will give an idea about how the engines are classified. So we have air breathing engine as well as non-air breathing engines. So non-air breathing engine has only one example, that is the rocket engine. And in air breathing engines we have IC engine and EC engines. This IC engine, by saying name, it means actually the internal combustion engine, and EC is external combustion engine. And by saying internal and external combustion, we keep in something comes in mind that the combustion is happening inside or outside. That gives a wrong idea as a matter of fact. So this definition of IC engine and EC engine has got changed to give a better consistent idea. We'll see that in the next slide. In the EC engine we have only one example here, that is steam engine. In IC engine we have two types of engine. One is the piston engine, which always walks along with the propeller, because piston engine itself cannot give thrust. It can only provide power which is available in the shaft. So that shaft has to be connected with the propeller to produce thrust. And in the case of jet engine we have these many categories. We'll see that. A new definition for IC engine and EC engine is that an engine in which working fluid itself takes part in combustion is called internal combustion engine. And similarly, the EC engine is the engine in which working fluid does not take part in the combustion is called external engine. This definition is more consistent and gives a good idea about the differences between these two engines, because even in EC engine, when you say external combustion engine, it doesn't mean that we burn do the combustion somewhere outside and then we bring it back inside the engine. In EC engine also the combustion happens in a confined environment, but that does not take part in the working fluid. The working fluid does not enter in the combustion. So this definition is more consistent when we differentiate these two types of engines. In EC engine we have an example of the steam engine. We can see that steam enters here and then it pushes this piston with a huge force. This piston piston start moving this to and fro, and this to and fro motion is converted into a rotatory motion using this crankshaft's arrangement, and this power is generated in this shaft, and this shaft can be utilized anywhere else. What is important here is that this steam which is entering is taken from somewhere else. is not the part of this power generation. It can be anything. It can be coal burning somewhere else, or somehow we are heating water somewhere else. So this basically is steam supplied from outside. That's the definition of your EC engine. Here is a small image showing the steam locomotive, in which the huge amount of coal is available here. This coal is burnt, and then this huge heat is generated. This heat generated is actually used to heat the water. Water turns into steam, and that hot steam is supplied to the piston movement, piston cylinder arrangement. So this a small part basically generates the power, and this whole thing is just we have to carry it. So this tells it that it's external combustion. Combustion is not happening inside. Piston engine, which is basically IC engine. So in this case, the working fluid, which is the air and plus air plus the combustion product. After combustion, the product of combustion is, in normal sense, water, the H2O, and carbon dioxide, because we are burning hydrocarbon. So hydrocarbon joining with oxygen turns into water and carbon dioxide if it is clean combination, if it is a very efficient combustion. Otherwise we'll have some more product there. This combustion product joining along with the fresh amount of air or unburnt air makes the working fluid. This working fluid itself takes part in the combustion. That's why it's called IC engine. Now this piston engine generates power, and that power is fed to the propeller, and this two combination of piston engine and propeller combination, they generate thrust. Here we can see that thing. The propeller, which is working against the airflow, sees two types of motion. One motion is associated with the vehicle motion itself, what you call free stream velocity. The vehicle is moving with a particular velocity, so propeller moves forward in the axial direction. It has another motion, which is actually the rotatory motion. It's rotating in the air, so it has a rotational motion in this direction. We can see this V0 is the velocity, axial velocity with which it is advancing in the air, and V2 is the velocity with which it's rotating in the air. So the actual velocity it sees, the relative air velocity is actually V1, which is the combination of V0 and V2. And then this is a aerodynamic shape, so it produces lift and drag, and these two forces are actually in the direction of perpendicular to the axis and along the chord line. These two forces together gives a combination of the thrust in the forward direction and the torque required to rotate the propeller. This is the basic combination and basic operation of piston engine and propeller combination. Now this engine has got some problems, like it gives vibration. Why vibration? Because the piston moves to and fro, so piston has to start from the rest and then accelerate to the high speed, then again start decelerating and then stops, then it goes in the backward direction, again it accelerates and then stops. So this to and fro motion gives a vibration kind of thing. It is noisy, it gives a noise because to and fro motion is a noisy operation. And the more important drawback it has is its forward speed is limited, because the propeller, which is producing thrust, sees two velocities, and the final velocity with which it is operating is actually higher than the forward velocity of the vehicle itself. So there are chances that the propeller reaches the sonic barrier before the vehicle itself goes there. It means vehicle may be moving at a subsonic speed, but the propeller may start operating in a supersonic range, supersonic velocity, and the moment it reaches supersonic velocity, it start encountering the shocks and all. I mean, the shock generates a lot of new problem comes there. the tip of the propeller has got the maximum velocity, the radial velocity. Hence, the tip is the propeller reaches the sonic barrier first if the velocity keep increasing. So the moment tip becomes supersonic, shocks are generated and they stall the performance of the propeller. We call that actually the tip stall. The tip stall comes, the whole performance of the propeller comes down, its aerodynamic efficiency comes down and drag increases. So we try to avoid that thing. So this limitation of the propeller gives a limitation of the piston engine propeller combination to be used only in the low performance, low speed vehicles. This was a big drawback. So people started thinking of new devices. So the gas turbine engine was the solution, which we call normally jet engine, because it is characterized by the hot jet coming out of it, which is not visible in the case of piston engine and propeller combination. Now let us see the jet engines. Jet engine basically works in the 4 block operations. One is compression. It compresses takes the air and compresses it. Then it goes for the combustion. The compressed air is sent into the combustion chamber where fuel is injected and they mix up together, and then combustion happens and huge amount of energy is added to the combustion product of gases, especially thermal energy, and then this is passed through the turbine where expansion happens. So part of the thermal energy contained in the combustion product gases are extracted, and that is fed to the compressor, because compressor has to run. So to run the compressor we have turbine. The turbine extracts the energy and feeds to the compressor. After that, when the flow comes out of turbine, it is still very energetic, it's very hot, so it expanded again in a nozzle where pressure energy or thermal energy changes to the kinetic energy, and then the exhaust is in the exhaust, the flow is thrown backward direction with a high speed, and that creates a forward motion, a forward thrust that is utilized, and that's how the thrust is created in the jet engine. Here is a small image which gives the idea about the basic operations taking place in a jet engine. First the compression happens. This is the symbol of a compressor. It's not the compressor looks like that. it's just a symbolical compressor. So when air comes, it compresses. The compressed air is thrown back into the combustion chamber where the combustion happens and a lot of energy is added to it, and then this energetic gas is let it pass through the turbine where some part of energy is extracted to run the compressor. You can see that compressor. Now the airflow coming out of it is still energetic, and that energy is recovered back by passing it through the nozzle where expansion happens and thrust is created because of the hot jet with high speed coming at the exit. Now you can have little comparison between the jet engine and propeller engine combination. So it operates on a small mass of air and gives large velocity change to it. That's what it happens. It takes a smaller mass of air and then mixes it up. Comparatively it's a small mass, and then it gives a large velocity change. And in the case of propeller engine combination, it works on the large mass propeller area. Propeller basically rotates and then it covers a large area in the air, so it operates in the larger mass of the air and gives a small velocity change to it. So in both the cases we have a change in momentum, because momentum is the combination product of the mass and the velocity. So we have a change in momentum. That change in momentum gives us the thrust. The thrust generated using Newton's second law of motion, where you can say the mv, that is the momentum. The time rate change of momentum is the force felt, and that's how the thrust is created in both the cases, whether it is propeller or it is the propeller piston engine combination or the jet engine. Now in the jet engine, here is a symbolical simple jet engine, which is basically turbojet engine. So we call it turbojet because it contains turbine and the jet is there, turbine required for running the compressor. Here compressor are many stages. We don't want to go into the details right now because that's not our idea to discuss at this moment. Why we have stages in compressor and why we do have stages in turbine, the separate discussion. I don't want to go right now. So intake is there, then compressor comes there, it compresses the air, then combustion happens in this area, and then the hot gases are passed to the turbine, and after this it is passed through the exhaust nozzle and thrust is generated. Now jet engine, which is actually using a simple gas turbine engine, also of two types depending upon the compression it can do. We can use the centrifugal type of compressor to compress it, or the axial type of compressor. Centrifugal compressor came first because it was easily available and easily conceivable. So it came here and it rotates and takes some amount of air, it rotates and it throws in the, because the centrifugal action, the air is actually thrown outward with a high speed, and then it gets compressed. Then that compressed air is passed through the combustion chamber. In the case of axial compression, a different type of phenomena takes place here. Centrifugal force is not working, it simply passes through the variable area, action takes place here and flow gets compressed, pressure goes high. They both have their own advantages and disadvantages. This looks very simple, but compressing to the very high pressure is not very easy in this case, because for that we'll have to have a very large impeller which can actually give a large compressive centrifugal force. In this case we don't have to have that. We can simply add more and more stages and we can get a very high compression ratio in this case. Both type of compressors are available. Earlier this centrifugal type compressor was leading the aircraft engines, but now almost all are using this axial type of compressor. Turboprop engine. Turboprop engine is just a simple engine which is gas turbine engine, which where we have more number of stages in the turbine, and at least one stage of turbine is fed to the shaft power, so that is used to rotate the shaft, and that shaft power is fed to the propeller. So in this case we are having two different devices which are actually, and two different mechanisms which can produce thrust. So propeller is producing thrust, plus the flow which is coming out of the turbine is still energetic, very hot, and it is passed through the exhaust nozzle where thrust is created. Something is to be noted here is that when the turbine power is fed to the propeller through shaft, we have a gearbox here. That gearbox has to be something to reduce the speed or the rotational speed of the shaft, because propeller cannot work at a very high speed. We have seen that already, because there are chances that tip can go in the stall region, and when tip stalls, the efficiency of propellers comes down, thrust generation comes down. We have to avoid that. So we reduce the speed at which the shaft is rotating. So we fed the power to the propeller at a reduced speed. In this case the power generation, thrust generation is shared, and 50% propeller, 50% jet. The thrust comes 50% from the propeller and 50% from the jet, which is still existing there, which is energetic. Heavy gearbox is required. That heavy gearbox gives some disadvantage to this combination. It adds extra weight, plus a lot of losses take place in the friction. That has to be taken care of with the nice lubrication and the maintenance time to time. That adds extra disadvantage to it. Turbofan engine. The turbofan engine, instead of power from the turbine feeding to the propeller, just add one extra fan there. In the turbofan engine, instead of using a propeller, another device which is called shorter in diameter and looks like compressor, which is called fan, is used. This made the engine little quieter and efficiency goes high as compared to turboprop. In this type of engines, the thrust production load on the jet is further reduced, and on the rough scale the fan produces almost 70% of the total thrust, while jet still produces rest of the total thrust. 30% total thrust is produced by the jet in this case now. Now it is clear from the above image that a lot of amount of air which fan operates does not pass all through the inside the engine. Let us see the image again. A lot of air which is actually ingesting, which this fan is operating in, doesn't pass through the inside the engine, so it goes over the engine. This has a lot of advantages. First of all, this air is cool air, so it reduces the temperature of the engine, so engine life goes high, and it has the structural health. Now this hot air, this cool air above it mixes up with the jet, so it also produces thrust. This kind of operation we call actually the bypass engine. A lot of air is bypassed and doesn't go inside the engine, take place in the combustion, so this is called bypassed engine, and it gives extra thrust. This bypass engine also has two types. We can have low bypass as well as high bypass engines. Depending upon the design and requirement, whatever we need, we design accordingly, and we can have whatever we want. In this case, the amount of the fraction of the total air which bypasses the engine can be low or high, and we can have as we need. Turboshaft engine is very similar to the turboprop engine kind of thing. We have the compressor, it's a jet engine, it's a gas turbine engine, so we have a compressor here, and then we have a combustion chamber, and the turbines are there. So at least one of the turbine is connected to the shaft. The shaft can be used to feed the power to anything, as a matter of fact, anything. In the aerospace operation, we normally have this kind of arrangement to run the rotor of the helicopter, but this can be used anywhere where the power is available in the shaft, and it is generated using the turbo gas turbine engine. Now let us look into the jet engine genesis, how it started, and where it developed, and what we have today, how it came into being. Jet engine started getting researched in so many places all together. Many places people work without even getting in contact with each other, but they were working on the same problem, and they came across almost a similar kind of information, and they have the same credit. Their work was genuine and original. They were not they are not copying from any other, or they're not plagiarizing. So the two more important countries in this place we'll mention is the England and Germany, where two most influencing force were Frank White in England and Frank Whittle in England, Hans von Ohain in Germany. They were trying to develop the jet engine. They have something in mind, and they were just working at it. In both countries, jet engine started in mostly academic theoretical studies in 1920s, and individual scientists like Frank Whittle and Hans von Ohain, they also started working. They both came up with the same design, the centrifugal flow jet turbine. In this engine, a compressor fan compressed air into several combustion cans arranged around it. The air was mixed with the fuel spray, ignited, and hot gases blown to the rear created the engine's thrust. So a simple centrifugal impeller compressor type jet engine were developed by these people, and they were having many cylindrical type of combustion chambers arranged around a shaft, and they were just using it to generate the thrust. Frank Whittle has a startup company called PowerJet, who was working with it. So Whittle and his company PowerJet made good progress with the engine, but his work suffered from the lack of official or corporate support. This guy didn't give much importance to him, so in the simple modern words, he found no investor for his startup project, and then he went financially broke, and he even suffered a lot of financial health health problem also, because he was not able to work properly. So mentally also he was having some problem. On the other hand, in Germany, Hans von Ohain got a good support from someone called Ernst Henkel. He was the one of the most important aircraft designer in Germany, and he was also major aircraft producer. So he got highly interested in the Ohain works, and he thought that he had an idea and vision that if the airplane has to go for a higher speed, jet engines are the only option. So he took a lot of interest in the Ohain work, and he allowed him to work in his own laboratory, and they both started working together. As a result of it, Henkel and Ohain made their first finish line, and on August 27, 1939, they were successfully able to make airplane and fly it with the propulsion of jet engine. That plane was told as HE-178. HE stands for Henkel, perhaps. It was produced by him. Then it was realized after working with the jet engine they have at the time, that high temperature and high rotational speed pose some serious challenges. They know that they are dealing with the real troublemaking system, and they have a lot of accidents. And the very first engine which Whittle produced actually gave a big it went out of control, and it got disintegrated. So it was a big troublesome job they were doing basically. And second problem they faced with the existing engine was the centrifugal flow compressor has some limitations. Now centrifugal flow compressor, if you want to compress the air using the centrifugal compressor, with the high compression ratio, you have to have a big impeller, and that big impeller will not come without any cost from the drag side. It will give a big blocking effect, so the drag will increase. And also the centrifugal compressor, air was actually coming to the axially first, and then it goes radially, and then again it has to come axial direction, and then it enter into the combustion chamber. That was not a very good design basically. It was giving a lot of trouble. So these two problems normally these guys were facing. So the solution was axial compressor. The people started thinking about axial compressor. So in this case, the Jumo, the Junkers Aero Engine Division, and the BMW Aero Engine manufacturer in Germany, they tried to pioneer the job. And again, Germany was not alone. Someone called A. Griffith, who was the British jet propulsion theoretician, he also started thinking of the similar kind of engine. Initially he developed a turboprop engine, and it was very successful for him, but then he gave up the turboprop and started working for the axial flow engine, where the impeller will not be required to compress the flow, and we can have the axial compressors. In late 1930s, a metropolitan vehicles firm started developing turboprop engine, but in 1940 they started working with the pure jet engine with the axial flow design. So they gave up the idea of working with the turboprop, and they thought, let us discuss and let us research and find the axial solution for this centrifugal compression. In England, Whittle and his startup finally received some support from the Air Ministry, and on May 15th 1941, the first British jet aircraft, the Gloucester E-2839, finally took to the air. It was powered by the prototype W.1 engine. So maybe the Whittle wanted his name. So Whittle prototype was W.1, and it successfully flew with the axial compressor. Then he thought of moving to the developing a improved W.2 engine and prepared it for series production. His company Powerjet didn't have a facility to produce. He was only trying to research there, so he didn't have any manufacturing facility. So the car manufacturer Rover allowed him to produce his prototypes there, and then finally it was actually given to Rolls-Royce and de Havilland for producing this engine. At this point, the British were lagging behind in technology, but they were leading in manufacturing. They were not thinking much towards the axial thing, and they were just going ahead with the centrifugal compression itself, and they were trying to make more and more advanced of this type, and they were doing nice production in this. Rolls-Royce was working to develop the technology, so he was working with the W.2, which was given a new name called Welland, and finally it was given another new name called Derwent, and they successfully developed a improved version of it. As a good effort by these people, the first operational jet aircraft squadron in history was the Royal Air Force 616 squadron came into being. The Germans were lagging behind in production wise because they concentrated more on the effort on the more advanced axial flow engine. This engine was more complicated and therefore took longer time to develop and make ready for series production. Its production was also difficult because of the special heat resistant metal is required, because it was creating huge heat in the combustion chamber. The huge technical challenge this type of engine posed are well demonstrated by the fact that centrifugal flow engine still powered the most modern jet fighters of the Korean War, the F-26 and MiG-15. So this challenge of developing a axial compressor was actually huge, and in the meantime the centrifugal compressor type engine kept developing and kept producing also. So people kept filling the gap till the axial flow engine comes into being. They kept using the compressor centrifugal flow engines. So only in 50s the axial flow engine became the most common type jet engine, and then we have the most advanced one, and after that axial flow engine took the job, and then development started happening in this engine itself with the further and more improvement in their functionality, operation and efficiency. Now let us look into the jet engine technological advancements we have seen in a past time. The first advancement we like to mention here is that variable area nozzle. To understand this advancement, let me have a small idea about the thrust generation the equation. This is the equation which can be derived using this momentum change inside the engine. We have the thrust available here. F is the thrust, and this is the mass flow rate of the air, and F is the fuel to air ratio, mass flow rate of the fuel to the mass flow of air, and V is the exit velocity, and V infinity the velocity with which the vehicle is moving, or the same velocity with which the engine is moving. So we have free stream velocity, AE the exit area, PE the pressure at the exit area, exit plane area, and P infinity is the ambient pressure. So now we have two parts of the thrust generation. This is called momentum part. Here's momentum part because momentum change is taking place here. This is the pressure part. So pressure change is causing the force to force to generate here. Here the momentum part is there. Now general idea is that we should have both as high as possible so that we can actually have large amount of thrust production, but the fact is these two parts are not independent. These two are interrelated. So if you try to go very high momentum change, the pressure change will come down, so this part will come down, and vice versa. That's what will happen. The question is which part is important. We find that the part which is more important is the momentum part. That's why we have a nozzle. We convert the pressure energy into the kinetic energy, and it has been found with the experience with the operation, and mathematically it can also be proved that the engine creates maximum amount of thrust when we have this part as 0. This part goes 0. So when the pressure part comes 0, we get the maximum thrust, and that at that condition we call it as a adapted condition. The thrust is adapted. The engine is working at the adapted condition. That's the most optimum thrust produced at the time. Now the question is, when the aircraft flies, it starts from the sea level to its operational height or design altitude. So its altitude changes. Pressure, the ambient pressure also changes at the altitude changes. We know that. Now in that case, how to make this part always optimum? Because P infinity is changing as the altitude changing, so we must change the PE also. And how it is possible? To have the optimum condition or optimum operation, we must change it. This is possible only if we change the area, the exit area of the nozzle, because that's what operates, that's what basically controls the expansion through the nozzle, and this expansion actually controls the exit pressure at the plane. Now this gives rise to a concept of variable area nozzle, so that we can have the optimum operation even at sea level and at the design altitude. This is a small idea about how the area can be varied. We have a small stripped plates here, which can be closed or which can be opened depending upon the requirements. So area can be increased or decreased as per the requirement, and we can have the most optimum output from the engine. Second one is the afterburner. Afterburner's concept is also very simple. When the air enters the compressor, we have compressor here, it gets compressed, pressure goes high, and this highly pressurized air is passed through the combustion chamber where combustion happens, and then it comes out of the turbine here. Now when it comes out of turbine, the entire combustion product or the gas coming out of it is not burned out. There's still unburnt air available there. This unburnt air can actually be used again by mixing with the extra fuel and burn it. This can give the high thrust. The thrust can be pushed to at least 50%. So this concept is used to boost up the thrust when time comes, when the requirement is there. This has a drawback that in this case the efficiency of the engine comes down drastically. So this is used only when there is a real requirement, especially when there is a question on the life and death. Suppose someone has fired a missile or the rocket on any fighter aircraft. That fighter aircraft will not care about this efficiency at the time. It will like to run away with a high thrust and high speed, so it engages the afterburner and doesn't care about the fuel efficiency. So for a certain amount of time, a huge thrust is generated, and then it tries to douse off the missile or rocket. This is one of the advancement jet engine has seen in the due course of time. Then we have ramjet engine. To cut down all the frictional losses, moving parts were removed. Moving parts available in the engine are jet engine are the turbine and the compressors. Compressors are required to compress the air, and the turbine is required to run the compressor. So these two parts are the moving parts, and then we have so many different stages to have the most optimum condition or optimum operation. These two moving parts cause a lot of losses. Friction losses are there. Someone thought, why not you remove these moving parts? When you remove this moving part, how the compression will happen? Because compression is required to do the combustion. So it was devised that the compression can be achieved by having a ram effect. When the air comes with a high speed and enters into a narrow region, and then it slows down, the pressure goes high, even there is no compressor there. This effect is called ram effect. So air can get compressed using ram effect, and then this compressed air can be supplied to the combustion chamber, and then combustion can happen, and then the entire hot gas, the energetic gas, can be actually passed through the nozzle without tapping off any power from it using turbine. Because turbine is not required because compressor is not there. This operation becomes something called we call it ramjet. The ramjet is the engine in which the compression takes place by the ramming effect. We have a small forebody or something like a spike here, which helps in doing the efficient compression or recipient ram effect. It has advantages, like the design is simple. It has removed all the moving parts from it, and compressor is not required, so turbine is not required. A lot of weight has been reduced. It is more fuel efficient, not compared to turbofan. It's more efficient compared to rockets. Try to understand. And it is very useful to run it between the Mach number 3 and Mach number 6. Mach number 3 is required because ram effect should be good enough to compress the air to provide a good sustained combustion. For a lower Mach number, it will give problem, and for a subsonic flight it cannot even walk. This is the disadvantage the ramjet engine has. It does not produce thrust at a standstill. So if it is not moving, there is no ram effect, there is no compression, no combustion, no thrust generation. So basically the ramjet engine cannot be used, and it becomes inefficient below Mach number 2. Even if the ram effect is there, compression is happening. So higher the speed, better it is basically. We can see a small comparison between the turbojet engine and ramjet engine. You can see that very clean and very simple. Just a body to compress it to do the ram effect, a center body or a spike body, and then we have a nozzle here. Here we have compressors, and then is many stages of compressors. Then we have some of the stages of the turbine. So it's basically heavy and also cause a lot of loss because of friction. It's more cleaner, but it operates only at the higher speed. Now another advancement, you can say, the people thought about the turbojet engine. Turbojet engine is developed because ramjet cannot operate at the lower speed. So some people thought that why not we have an engine which can operate like a turbojet engine at the lower speed, and when the speed is good enough to produce the ram effect, the same engine can be converted to a ramjet engine. So there is small turbojet inside a big ramjet engine, and then flow comes here, it enters into this thing, and flow starts, and the thrust is produced. We have a turbojet available here. Now when the speed goes high and ram effect is good enough to give the compression, then the compression inside the turbojet is not required. The flap closes this entry, and the flow goes over this turbojet, and the entire body starts working as a ramjet engine because compression is good enough. This kind of engine was actually used in the SR-71. Now Scramjet engine, another advancement in this thing. A simple mechanism of the ramjet is shown in the picture. Air comes and then it starts ramming, so pressure goes high, and pressure goes high, then this high pressure and the velocity comes down, and velocity comes down to even subsonic speed, and then combustion happens here, and then finally nozzle is here, so exhaust happens. Now pressure here, the flow here, the flow properties here basically are determined by how much the compression is done here and what is the speed in the free stream. Compression basically reduces the flow and reduces the flow velocity and increases the pressure, but question is how much? If the velocity at this level is very high, very high, then even by reducing the velocity here, it is possible that the velocity in this region, in the combustion chamber, combustion section, is still supersonic. Then you have a problem. Combusting a supersonic flow is not easy. Flow will extinct, the flame will not hold, so we have a problem there. So a new concept was developed of the Scramjet engine. The name itself tells actually is the supersonic combustion ramjet. It works like a ramjet, but the combustion is at the supersonic speed, and this is required because we want to go in the hypersonic era. Supersonic era is almost over, and I believe that aerospace is the future of humanity. If the humanity had to survive, aerospace has to progress, and hypersonic is the future of aerospace. So the hypersonic flights are going to be very normal, very frequent, and very common in a coming future. But that is possible only if we have a scramjet engine. So a scramjet engine is the another advancement jet engine going to see, and people are working at it to make it more efficient. In a scramjet engine we have a small inlet, isolator, combustor, nozzle is there. Isolator is something looking like new part here. So isolator basically is a arrangement here which prevents the heat generated and the flame and the fire generated in the combustion chamber. It prevents it from traveling into the upstream direction, and it also prevents the heat damaging the body of the engine there. At the final, the last advancement I'd like to discuss here is the ceramics and the composites, the use of ceramics and the composites. When we try to research and improve the performance of any device, what we normally need is either we improve its output or improve its efficiency, or sometimes we try to research and see what comes next. Maybe something new will come which is completely unknown to us. In the case of improving the performance, we can have the ceramics, use of ceramics in the combustion chamber area, which can become lighter compared to the metallic alloys, and can be more heat resistant, so it can give a better performance there. And composites can be used in the manufacturing of compressor especially, and this can reduce a lot of weight, and this can help in improving the aircraft engines. So that's all I have as a demo. So thank you very much, and any questions if you have, you can write me at the email. Thank you.